amplitude modulation, converting the electrical signal into optical signal. All right. Now, historically, this material has been used for actually many decades, not only just because of the Chi2 or electro-optic coefficient, but also it's a very nice linear optical material, has very low optical loss, and is widely transparent from visible to all the way to mid-infrared frequencies. So not only has been used for long-distance telecommunications, but also for microwave photonics and also for quantum and nonlinear photonics. But the one problem is that with this lithium niobate material is that whenever people talk about this material, they will say that it's a great material, but it's just not compatible with the concept of photonic integrated circuits. And the reason is if you look more detailed into the material or the waveguides, the waveguides of lithium niobate traditionally are formed by diffusing ions like the titanium ions into the lithium niobate crystal. And by doing that, you can create an index contrast of about 0.02. And that small index contrast means the waveguide size are pretty large and they can barely bend, bending radius on the order of a centimeter scale. So really, you can't do much on the chip like what people have been doing in, for example, silicon photonics. Right. And more of a problem is that when you make an electro-optic modulator, as I just said, you need to apply voltage across the waveguide, right? Now, because the waveguide is so large, you have to put the electrode far away from the waveguide so that at the same voltage, right, with a large gap, you only get a small electric field and a small electro-optic efficiency. Right, so the whole idea of this field of thin film lithium niobate is trying to build devices that are similar to silicon photonics, right? So in silicon photonics, you have SOI, and here we're talking about LNOI, where you have a thin lithium niobate film, few hundred nanometers, single crystal sitting on top of silicon dioxide, right? So that gives you a very large index contrast and much better light confinement and the smaller banding radius. Most importantly, because of the small size of these waveguides, you can now put the electrode much closer so that induce a much larger electro-optic and nonlinear optic efficiency, right? So this is just one example of the devices built by us compared with a traditional modulator you would buy from the market. And on that chip, right, as I mentioned, you can do a lot of different things, micro ring resonators, and these are comb generators, these are tunable filters, many different things that really makes it a circuit. Right, so a little bit more about how we do it. So basically, we rely on this LNOI wafers, and quite fortunately, nowadays we can get these wafers on 4-inch up to 6-inch wafers scale, and these are single crystal made of ion slicing. So all we need to do is to make a planar lithography and dry etching process to make these photonic wires. Right, but one complication here compared to silicon photonics is that the dry etching of lithium niobate is relatively more difficult. Right, so at the beginning, so there's also part of the community pursuing so-called heterogeneous approach, right, where you would include different material, for example, silicon nitride, to form a rich waveguide. So by doing that, you can get rid of the need to dry etch lithium niobate, and also potentially compatible with standard CMOS foundry processes. But on the other hand, because only part of the optical field sits in lithium niobate, it compromises the electro-optic or nonlinear property of lithium niobate. So from the beginning, actually, we have, this has been about 10 years now. We kind of decided to directly go for the monolithic approach, and actually, once this dry etching process is figured out, you'll see that the process could be quite repeatable and reliable, and most importantly, has low loss because of the actually the material itself is really nice. It's highly transparent. So today, if we look back, right, throughout the years. You can see that the quality factor of these so-called dry etched lithium niobate resonators, which directly translate to the optical loss, has been increasing steadily on the log scale, right? On the log scale. In the early days, you can have these dry etch devices could have loss as high as 100 dB per centimeter. And later, right, as of this was our results at the end of 2017, we're able to demonstrate resonators with Q factor over 10 million, and that correspond to propagation loss of 0.03 dB per centimeter. Right. So as I mentioned, I joined City University of Hong Kong in 2018, and nowadays we are also able to use in-house fabrication facility to produce repeatably these devices with Q factors over 3 million and the loss of less than 0.1 dB per centimeter. And the most important difference from what I was used to doing at Harvard is that we are doing this nowadays using the photolithography process, using the UV stepper process at Hong Kong UST, and the rest of the process are done at CityU. And you can find that we can build devices on the whole 4-inch wafer. We can do 6-inch if needed, but we just in the laboratory, we don't need that volume yet. And you can build all kinds of devices on the wafer with a low loss of less than 0.1 dB per centimeter. So this work was mostly led by my former postdoc, Song Zhao. And not just us, right? There are there's an entire community pursuing these thin film lithium niobate devices, and here is just a glimpse of the modulators built by different groups, including some of the more advanced capacitive loaded modulator designs. And also, really, the material enjoys a lot of different properties like electro-optics, nonlinear optic, Chi2, Chi3, and also piezoelectric. So also a lot of other functional devices based on the variety of material properties in lithium niobate. And so that basically tells you where we are and the platform we have. And so based on what we have, I'm going to show you a few different devices that we aim for different applications. So the first thread is for high-speed optical communications. And as I just mentioned in my introduction, the most important application would be a electro-optic modulator. Right? So this is a typical electro-optic modulator we build on this thin film lithium niobate platform. The configuration is very simple. It's just the Mach-Zehnder interferometer. This is optical Mach-Zehnder interferometer. These very thin lines are the optical waveguides. And then you build RF microwave electrodes with traveling RF fields going along the Mach-Zehnder interferometer that is the modulation electrode, right? And the most important thing is that now, because the waveguides are much smaller, you can put the electrodes much closer. So that gives you a much smaller drive voltage, right, or higher electro-optic efficiency, which is measured by the so-called voltage length product, right? It means that at the same length, how much voltage do you need to drive this modulator or switch this modulator from off to on. Right, and we find this product to be about an order of magnitude smaller than the traditional bulk lithium niobate modulators, and that 2 volt centimeter number means that nowadays you can build a device that is only about 1 volt with a small distance of about 2 centimeter, and so this is a device we actually measured. Right? So if you go from off, right, transmission off to transmission on, you only need about 1.4 volts, and that means actually, for system applications, you can get rid of the amplifier, right? Initially, you need an amplifier to match the CMOS voltage with a traditional lithium niobate modulator, but now you can get rid of that amplifier, directly link CMOS with the LN chip, right? So that means you can build systems with electro amplifier free operations. So that is a big deal for power consumption of optical communication system. Now, power consumption is one thing we care a lot. The other thing we care a lot is the bandwidth, right? The speed of these modulators. And the bandwidth actually depend on the so-called velocity matching condition, right? Essentially, here you have optical wave traveling and microwave traveling at the same time. You want the 2 waves to travel at the same speed so that they can constructively modulate over the distance. Right, and it turns out that in thin film lithium niobate, it's much easier to do the velocity matching because for bulk lithium niobate, the RF, the refractive index or dielectric constant of lithium niobate is much larger than at the optical frequency, right? So it means that the traveling speed of RF is intrinsically much smaller than optics. But in thin film, the nice thing is that you have many materials stacked, right, many materials as a stack, and so that you can engineer this stack, and also you have a low index oxide, which has a much closer index compared to the optical index of lithium niobate. So that means it's much easier to achieve velocity matching here, and we were able to demonstrate. This was a few years ago now. At the time, were able to demonstrate devices with 3 dB bandwidth of about 100 gigahertz at the time. So later I'm going to show you that actually these devices can go much beyond 100 gigahertz according to our recent work. Okay, so this is a modulator for communication system, and a question we can ask is that what else can we add to this communication system, right? And so we previously demonstrated the modulator, and another thing I think we can contribute to this whole system is the frequency combs, right? This is an important concept for wavelength division multiplexing systems. In the old days, you would need many lasers to drive these WDM systems, and but recently people find that you can actually make use of a frequency comb, which means you have equally spaced frequency components in the frequency domain, right? And then you can use these different lines as sources for the different wavelength channels. So we asked that whether we can build frequency combs based on our platform, and especially based on the nice electro-optic modulators we had. Right. And the answer is yes, because people have always known that if you do phase modulation to an optical wave, right, you will generate sidebands, and it's spaced by the modulation frequency. And if you overdrive a phase modulator, right, these basically give a very high driving voltage. These sideband generation process can actually cascade, right? So you can generate more sidebands, and that basically gives you a frequency comb, right? And in fact, a few years ago, we did this experiment where you just make a thin film lithium niobate phase modulator. And the only difference is that from the previous device is that you don't have a Mach-Zehnder interferometer, but instead you have just goes through the modulation area once. And if you drive it hard enough with 3 watt of RF power, you get 28 lines. So pretty broad, right? But the problem is that the RF power is quite large. 3 watt is not quite practical for a system application. Right, so we start to think whether you can actually reduce the RF power consumption, and one idea here is that because, as I said, the system has very low optical loss, right? But if this optical signal only goes through the modulation area once, then it actually is a waste of the optical loss property, right? So one thing you can do is that you can make a so-called resonant EO comb by using the high-Q racetrack microresonator and put the modulator inside that resonator. Right? Then, because the resonator has a very long lifetime, this modulation can cascade for many times. Right? In the frequency domain, basically, it means that the modulation frequency is matched to the FSR of the resonator. Right? And we also did this experiment a few years ago that you can actually put one input optical signal and turn the modulation signal on, and you can see this comb generation process is very efficient. This entire comb is generated with 900 comb lines spaced at 10 gigahertz and with an optical bandwidth of more than 80 nanometer. Right, and the most important difference for these EO combs compared to Kerr combs is that the EO process is a more linear process, so that actually there's no threshold. So it means that if your input optical pump signal increase and decrease, the comb shape will not change. It will just go up and down depending on the input frequency. Right. So this is really nice, really broadband, but there's one problem with this as well. The main problem is that because you use the resonant structure, It means that you have limited optical and RF tuning range or bandwidth, right? More specifically, your optical signal has to be exactly matched to the resonance, and the RF signal has to be matched with the FSR, right? So that is has some tolerance issue if you try to put this into a system. So we've been thinking actually whether we can combine this idea and this idea by actually still reusing the optical power in some way, but without the use of a resonator, right? So in the recent work, we actually shown that you can do that. And the idea is that you're still circulating the power, but without a resonator. And what we do is that you first modulate the signal. So first goes through this phase modulation area. So that's the first time, just as before. But now instead of going out, you loop it back. And then use the mode multiplexer to convert it into a different mode, a TE1 mode, which is orthogonal to TE0. So it doesn't affect the two modulation process doesn't affect each other. And then it goes through the modulation area again, and then it doesn't go out yet. It goes to the bottom because for this ground signal, ground electrode, you have two modulation areas. So it goes back and do a third modulation in TE0 mode, and then you do another loop back and go into TE1 mode for a fourth time, and before it goes out. You need a crossing here, which we also designed and fabricated here. And by doing that, you can, in principle, reduce the voltage by 4 times and RF power by 16 times, right? And a lot of the things actually is made possible because of this wafer scale fabrication process, which is much more repeatable and uniform. So you can see that the entire device, right, has many loops, and in fact, it's quite complicated, but very I think quite intriguing is that it actually works, right? So we actually made 4 types of devices. One is just a simple phase modulator, and then we also have this 2 types of phase modulator with 2 loops. One is that it only goes through the same mode, but for 2 loops. And then the other one is that it only goes to the top part, but in 2 different modes. And the finally is our 4-pass modulator. And so you can see that at the same drive voltage, our power of 0.6 watt, which is much lower than the power I just shown you, right? And you can generate only 15 lines in this first type, and then you can generate about 25 lines in this double pass, and you can generate 47 lines, right? More lines than the one I just shown you with a much lower RF power, right? 47 lines. And the nice thing is that this system is relatively insensitive to repetition rate tuning, and it's broadband optically, right? You can there's no resonance. You can basically put the pump signal anywhere, and you can generate generates these combs at different optical wavelengths. Okay, so that was our main a few devices we made for optical communications. The other important application regime I'm very interested in at this point is microwave photonics. So the idea of microwave photonics is that we are trying to make use of optical devices and techniques to help solve problems in the RF domain, especially at a high speed RF. You'll have a lot of issues with the traditional electronics, and actually there have been a lot of um, very interesting demonstrations in different areas, including signal generation, transportation, filtering, and also radar systems. The main idea of microwave photonics is that you basically convert the microwave signal into optics, right, using the modulator, and then you can do a lot of things, including transmission or signal processing using the optical toolbox. Right, and a big trend in microwave photonics is that people also want to achieve a lot of these system applications in an integrated format, or in an integrated photonic chip, right? So what we are thinking is that actually our platform is very nice for achieving these so-called integrated microwave photonics. The reason is that we have a high performance EO modulator, which is needed here. We also have a low loss signal processing network that can be used here, right? So that's why we think this platform is really nice for an ideal microwave photonic chip, right? The only difference when we look at the modulator is that for microwave photonic system, the requirement is a little bit different. You actually need a highly linear modulator because a lot of times you're dealing with analog microwave signals, which means the linearity of this modulation process directly translate to the system performance. And this is actually a problem for the Mach-Zehnder modulator I just shown you, because you know that when you translate the phase information into amplitude in a Mach-Zehnder, it actually is a sinusoidal function, right? Although usually we bias here and it looks like it's linear, but in reality it's sublinear. And with the third order intermodulation distortion, it means that if you input two signals F1 and F2, two frequencies, you'll get these IMD3 at 2F1 minus F2. Right. So our idea here is that to make use of a so-called ring-assisted Mach-Zehnder modulator, or RA-MZI, by combining MZI with a ring resonator, we know that at the off-resonant point of a ring resonator, the amplitude almost is a constant, but the phase actually goes through a superlinear relationship. Right? So if you design these two well and combine them as a so-called ring-assisted Mach-Zehnder, the ring basically couples to the Mach-Zehnder, you can actually compensate these two and then induce a so-called linearized transfer function. Right. And the really nice thing here, actually, this is not a new idea. People have done it in silicon photonics and indium phosphide. But the really nice thing about lithium niobate RA-MZI is that unlike these other materials, the material electro-optic response in lithium niobate is intrinsically linear, right? So the system is extremely simple but effective, so that you can only use a simple linearization strategy and to compensate for all the nonlinearity. While in other platforms, you not only need to compensate the nonlinearity from MZI, but also compensate the nonlinearity from the materials. Okay, so this is actually a device we built. You can see it's just this is a microscope image of the device. This is the ring resonator, and this is the Mach-Zehnder interferometer, and you can immediately see that the transfer function, optical transmission, as a function of applied voltage, it's much more linearized now. It's much more linearized, and compared to the same Mach-Zehnder modulator we fabricate on the same platform, you can see that it's a sinusoidal shape, right? It's much more linearized. And more quantitatively speaking, the most important parameter we are interested in is the so-called spurious-free dynamic range. And that basically means the signal, the dynamic range between the signal, which has a slope of 1 between input and output, and the modulation distortion, right? The mid distortion. And the really nice observation here is that because we actually have fully compensated for the third order terms, in our device, RA-MZI, this red curve, you can see that you can only measure the distortion with a slope of 5. It means that all the third order terms have been suppressed, right? And that gives you a much larger dynamic range of 120 dB hertz compared to the reference MZI modulator. Right? So you're talking about 18 dB improvement over reference Mach-Zehnder interferometer. Right, and as far as we know, it's also the highest SFDR ever measured on the integrated RA-MZI in any material platform. Right. So the last few minutes, I would like to go a little bit beyond the traditional microwave photonics. And one thing we've been thinking is actually, can we go beyond microwave, right, to so-called millimeter wave bands? And because we are trying to solve problems for microwave systems, and usually these problems become more difficult to solve it at higher frequencies, right? So if we can actually cover the entire up to 300 gigahertz, then we can do a lot of things in the millimeter wave domain and initiate the field of millimeter wave photonics, right, including 6G millimeter radars and a lot of things, right? But one thing is that previously, as I shown you, our modulator only go up to 100 gigahertz, right? So one question we've been asking ourselves is that, can our modulator actually go up to 300 gigahertz, cover the entire millimeter wave band? right? And so the key question is that whether our modulator can go beyond 100 gigahertz, right? So and we start to look into the requirement for millimeter wave optical modulator, right? And actually the requirements are the same. You need low RF loss, you need velocity matching, you need impedance matching. So same rules, but everything is more stringent because of the smaller wavelengths, right? And the more difficult part is that even taking the precise electrical measurements of these things are difficult at 300 gigahertz, right? And most of the previous work has been based on untested extrapolation from untested models at low frequencies, right? So we actually take advantage of our sticky laboratory of terahertz and millimeter waves, and we actually measured the electrical performance up to 300 gigahertz, right? So that allows us to extract the actual RF loss and extract the real velocity, right, to fine-tune our models and the impedance. And with that fine-tuned models, right, we actually can build a device that's optimized for millimeter wave applications. And more importantly, we build an in-house setup that can measure the electro-optic response up to 330 gigahertz, right? So this allows us to go fiber in, fiber out, the millimeter wave probes in and out, right? So with that, we are able to measure these electro-optic response at very, very high frequencies. Because of time, I think I'll go through this pretty fast. But the really nice thing is that although the RF Pi, for example, does go up a higher frequency, but in a relatively controllable way, and you're talking about 7.3 volt, pretty practical, even at an extremely high frequency of 250 gigahertz measured. And if you look at the relative modulation efficiency, or EOS to 1, you'll find that the shorter device will actually give you a 3 dB bandwidth of 170 gigahertz and 6 dB at 295 gigahertz. Okay, so because of time, I think I'll not talk too much about it, but you can find more details in our recent publication. Okay, and so to briefly summarize, I think we are looking at a platform, right, with really nice three things, a combination of mass, like wafer scale fabrication, right, very low optical loss, and also very unique electro-optic and nonlinear properties, right? And I've shown you a few different devices, comms, modulators for optical communications, and the high linearity modulators and 300 gigahertz modulators for microwave and millimeter wave applications. Okay, so so the linear modulators is